Welcome everyone, and thank you for joining us for today's presentation, Improved Mass Imputation and Probability Samples via Adjustment of Imputation Models Based on Non-Probability Samples for Selection Bias with Dr. Brady West. Today's presentation is brought to you by the Social, Behavioral, and Economic COVID Coordinating Center, or SBCCC, at ICPSR. For those of you who are not familiar with us, we are a center for communication, collaboration among NIH-funded projects undertaking social, behavioral, and economic research related to COVID-19. And so with that, it's my pleasure to introduce our speaker today. Dr. Brady West is a research professor in the Survey Methodology Program at the Survey Research Center at the Institute for Social Research of the University of Michigan, Ann Arbor. He earned his PhD from the Michigan Program in Survey and Data Science in 2011 and was elected as a Fellow of the American Statistical Association in 2022. He conducts research in total survey error and survey estimation more generally, and his current research interests include selection bias in surveys, responsive and adaptive survey designs, interviewer effects, survey paradata, and multi-level regression models for clustered and longitudinal data. So with that, I will turn things over to you, Brady.
Okay, thank you, John. Okay, I'm going to go ahead and share my slides. I think these slides may or may not be made available. I tried to follow all of our digital accessibility requirements, and I think I passed most of them, but I guess it depends on whether or not you can share them. So, I'll continue to remediate them if it's still a problem. But I'm happy to share these slides by email, if anybody would like to see them. So my email's up here on the first slide. So I'd love to hear from you by email if you have any comments or questions about the material presented today. I'll repeat the title, and then I have a little slide dedicated to that title, so we'll come back to that. But the goal here is to talk about improving the idea of mass imputation in large probability samples by adjusting the imputation models that are fitted to non-probability samples for potential selection bias. That's the general goal of this overall work, and I'll come back to that title here in a second. Okay, I do want to acknowledge my close colleague Rebecca Andridge from The Ohio State University. We've been collaborating on a number of projects recently, and we collaborated on this as well. This work was supported by an R03 grant from NCI, of which Rebecca is the PI, so I wanted to formally acknowledge that to start with. So coming back to that title, again, there's a lot of words there, there's a lot going on. I just want to summarize exactly what this talk is going to be covering. It's important to recognize that all imputation models are ultimately fitted to selected samples. So even if you're doing imputation in a given data set, you're only fitting those imputation models to the cases with complete data in that data set. So ultimately, you're looking at a selected sample, and that's what you're using to fit that model that you're then using to impute other missing values. So there's always this risk of bias in estimates of these model coefficients when you're fitting those models to these selected samples. In the more general setting of so-called mass imputation, and I've included the reference to Kim and colleagues here, there's a reference list at the end of the slides. You're fitting an imputation model to some selected sample that has all the variables that you're interested in, including usually some outcome variables. And that's often in a non-probability sample or some sample of convenience. And then you're using that fitted model to impute literally 100% of the missing values on that variable of interest in some external probability sample that you've attached to this non-probability sample. And the idea is you have common covariates, common auxiliary variables in both samples that can be used to predict that outcome variable of interest for every case in the probability sample. So clearly, we need a really good predictive model in order to execute this idea of mass imputation. Idea being, if you have a good model, you can then generate unbiased population estimates of models or descriptive parameters, whatever you're interested in, based on that probability sample with this new variable that's been completely imputed added on to the probability sample. So that's the idea. But the concern, again, is that you're fitting this imputation model to a selected sample, and the coefficients in that model that you might be using to impute that variable of interest could be subject to selection bias. So how can we fix that up in practice if we're trying to improve the quality of those imputations and subsequently inference that's based on that imputation model. That's the idea of the overall approach here. So just by way of background, mass imputation, as I introduced, is one possible approach for integrating non-probability and probability samples, and that's a really hot topic right now among methodologists and survey statisticians, is how we can combine different data sources to improve our inferences. And the effectiveness of the mass imputation idea relies on the assumption that the imputation model is transportable from the non-probability sample to your probability sample. So the same model holds for both the non-prob sample and the probability sample where you're making these predictions. If the selection mechanism that gives rise to your non-probability sample where you're fitting the imputation model is non-ignorable, that transportability assumption is likely to be violated and your estimated imputation models may be biased. And then down the road, the subsequent imputations in the probability sample may be very poor, and inferences that are based on those imputations may in turn be erroneous. So that's what we're worried about, and that's what we're trying to fix up with this particular work. So prior work on this problem has focused on the case of probability samples where the selection is largely ignorable, or the case of balanced sampling, which is another way to produce multiple data sources that are in some sense balanced on covariance of interest. Our focus with this work is what to do when these imputation models are fitted to non-probability samples or volunteer samples or convenience samples, whatever the case may be. So there have been many other methods that have been developed for making finite population inference based on some combination of non-probability and probability samples. So we also sought to compare our proposed approach to all of these other methods. So that was an important part of this work, is to acknowledge that yes, there are many other approaches out there for combining non-prob and prob samples, and we want to see how well our method did in relation to these other approaches. So just to introduce some notation, I'm not going to focus too heavily on a copy of the paper or the relevant papers to dig into these details. So I'm not gonna go through equations in a lot of gory detail as part of this presentation, mainly because of time. But I do want to introduce some of the notation so everybody's on the same page in terms of the notation that we're using. So the idea is that a researcher wants to make inference related to the mean of some variable of interest y in a finite population of size capital N elements. And that researcher obtains a selected non-prob sample of size little n from this finite population, and the individual elements in that sample are indexed by I. In that non-probability sample, y is the dependent variable of interest, and the measurement of y is unique to that selected sample. So we don't have y in the companion probability sample. Okay? Z represents a vector of scientifically relevant predictors of y, and those are the z variables that we're going to be using for imputation. So those z variables define the predictors that we want to use in our imputation model to predict y in the external probability sample. A is a vector of variables that are not of primary interest to the researcher, but may still be correlated with that variable of interest y when you condition on the predictors that are of actual interest denoted by z. Okay, so I'll come back to the A variable idea here in a second. And the microdata on Y, Z, and A, again, are only available for the selected non-probability sample. So we don't have Y in the probability sample, but we do have Z and A. Okay, so that's important to recognize. So the researcher then also finds a large probability sample that was selected under an ignorable mechanism from that same target population. And that large probability sample, again, includes Z and A, microdata on Z and A, but not Y. We also have a dummy variable S that indicates sample membership. So it's a 1 if you're selected into the non-probability sample, and a 0 if you're selected into the probability sample, again, under an ignorable mechanism. The researcher wants to impute the values of y for all units in the probability sample, which will allow them to make inference about that mean. And they want to use an imputation model fitted to y that includes the z variables as predictors. The researcher is then going to base their finite population inference on the predicted values of y in the probability sample under that idea of transportable, under the transportability assumption. The researcher can also use the weighted probability sample then to compute estimates of means, variances, and covariances of the predictors and auxiliary variables denoted by ZNA for that finite population of interest because, again, you have microdata on ZNA in the probability sample. So we can do that with minimal sampling error to get those sufficient statistics based on the larger probability sample as representing the larger target population under an ignorable selection model. So again, about those A variables, clearly the researcher could include those auxiliary variables A in the imputation model that's fitted to the non-probability sample. They're there. I've made the argument that they should be related to Y. Okay, so why not just do that? We're going to demonstrate that those auxiliary variables are more important for reducing the selection bias in the relationships of the Z variables that are of most importance to the person imputing the Y variable than as additional predictors in an imputation model for Y that's severely limited by using biased estimates of the relationship of the Z variables with Y. So in other words, the A variables play a more important role in adjusting those coefficients of Z for selection bias than they do as predictors by themselves in that imputation model. Okay, that's going to be one of our key points here. Okay, so here's the general adjustment approach. This is based on an earlier 2021 article in the Annals of Applied Statistics where we talked about the general problem of adjusting regression coefficients in selected samples for non-ignorable selection bias. So here's the general idea. You start by defining an auxiliary proxy variable for that dependent variable of interest Y from regressing Y on both Z and A in the non-probability sample. So that proxy variable, which we're going to denote by X, is based on the linear combination of those auxiliary A variables and their coefficients in that fitted model. So the higher that conditional correlation of X and Y, the better the performance of these adjustments. So we definitely want those A's to be relevant predictors. They might not be of direct interest in the imputation model, but we still want them to be relevant predictors. So given that auxiliary proxy variable X, you then specify a bivariate normal pattern mixture model, which I'll call a PMM, for X and Y, given the covariates of interest Z in the imputation model and the sample indicator S. The parameter that you see here, phi, is an unknown sensitivity parameter, and that helps to identify the other parameters in this pattern mixture model, which gives you a unique set of means and variances and covariances for both the non-prob sample and the probability sample. So adding that parameter phi to the model allows us to identify the parameters for the cases in the probability sample, where again, we don't have Y to begin with, okay? So you see a general function that describes the probability of being selected into that non-probability sample as a function of of X and Y, and phi dictates the nature of the non-ignorable selection. So you can see the role of phi in defining the probability of selection here as a function of the outcome variable of interest Y or that auxiliary proxy X. Okay, so you then adjust the coefficients of interest and the residual variance in your imputation model. That's a key point here. We're adjusting not only the regression coefficients in the imputation model, but also the residual variance, given the nature of the selection bias, according to the fitted pattern mixture model. And all of the values in these equations for performing these adjustments and computing the coefficients for the probability sample can be determined from the available information and given a choice of phi. So we need to have some choice of phi, again, in order to identify these parameters. And given that in the information for our selected sample, we can then compute each of the adjustments that you see here. So you see these additional terms that are being used to adjust the coefficients and the residual variance based on the selected sample, denoted there by 1. So we're looking at the values of these coefficients and the residual variance for the 0 sample, which is the probability sample in this case. And all these other pieces can be computed using that known information. So we can use a fully Bayesian approach with initial uniform 0-1 draws of phi to select the draws of each of these different parameters. So we can be fully Bayesian with this approach. And then given draws of the imputation model parameters relating Y to Z, we can then compute predicted values of Y in that probability sample, draw values of Y from the predictive distribution, given the residual variance and given these regression coefficients, and compute one value of the mean of interest. Then we repeat this process for many other draws from the posterior distribution. Then we get many possible values of that mean for many different replications of this prediction process, and we can make inference based on that distribution of all the draws of the mean of interest in the probability sample. Okay, so again, just kind of summarizing that, given the adjusted draws of the coefficients and the residual variance for the probability sample, we draw imputed values for each case in that large probability sample, and we compute finite population estimates of the mean of interest, generally using the weights from that probability sample, so we're getting an unbiased population estimate. And then we repeat this process a large number of times. That gives us many draws of the weighted mean for making inference about that finite population mean under this approach. And we're calling this approach PPMM-reg, so proxy pattern mixture model regression. That's what that name there stands for. Refer to this approach for imputation when we're comparing it to other approaches that could be used to make inference about that finite population mean on Y. So I mentioned we wanted to compare this approach to other competing approaches for dealing with this combination of probability and non-probability samples. The first one that we wanted to consider was the standard mass imputation approach under that transportability assumption, where both Z and A are used in that imputation model, okay, to make predictions in the probability sample, and we can do variance estimation using linearization or bootstrapping. I'll call that MI in the analyses that we're performing for mass imputation. Approach 2, a pattern mixture model based standardized measure of unadjusted bias. So previously, I actually gave a seminar in the consortium about the use of these measures of non-ignorable selection bias to compute estimates of descriptive quantities like means and proportions. That's what I'm referring to here. So this SMUB adjustment is a way of computing an estimate, an adjusted estimate of that mean based on the non-probability sample using aggregate information on Z that comes from the weighted probability sample. So that's another competing approach that we could use here. I want to note up front that the SMUB approach will only give you an estimate of a mean. One of the advantages of the PPMM-reg approach is that you actually get imputed values in the probability sample. So once you have those imputed values, you can do whatever you want with the data in the probability sample. The SMUB approach is designed only to give you an estimate of a mean overall. You're not going to get imputed values in the probability sample. That'll open up other analyses. Okay. The third competing set of approaches are doubly robust estimators of the means for non-probability samples. There's a growing literature on the use of these estimators, but they do also assume transportability in terms of the models being fitted, and they use that probability sample as a reference sample. The fourth approach is quasi-randomization based on inverse propensity weighting for the non-probability sample. That again uses the probability sample as a reference sample, and unlike the doubly robust estimators, this weighted approach is not doubly robust. Okay, and we'll talk about that as the IPW method. And then fifth, we wanted to consider these recently discussed shadow variable approaches. These approaches rely on an auxiliary shadow variable that's assumed to be correlated with the outcome of interest Y, but is independent of the selection mechanism when you condition on Y and a fully observed set of covariates. So we have this unique auxiliary variable that has nothing to do with selection, but is a good predictor of Y. And we can use that to make inference based on non-probability samples as well. Okay, so in doing this work, we learned a lot about the shadow variable approach. It is pretty new, but we learned that it's actually a special case of what we're calling this PPMM-reg approach. If you only have a single A variable, which is what the shadow variable approach assumes, you have a single auxiliary variable that can play this role of a shadow variable, and that's the auxiliary variable that we would need for the PPMM-reg approach. If you use A as a shadow variable and it has the properties I just described, you get almost identical results to the use of the PPMM-reg approach with that phi sensitivity parameter set to 1. And in the PPMM-reg approach, when phi is 1, that means purely non-ignorable selection. That means that selection is entirely a function of that Y variable when you also have that proxy variable X as a function of the auxiliary information available as well. So phi equals 1 is like the extreme non-ignorable case. And we found that we got almost exactly the same results, as I'll show you, as when A is a shadow variable. Okay, so both PPMM-reg 1 and the shadow variable approach will produce unbiased estimates of our mean if A is truly a shadow variable. So it's independent of selection once you condition on Y and Z, and it's predictive of Y. But if that A variable is associated with selection, even after conditioning on Y and Z, then the shadow variable approach is going to produce biased estimates. And in that case, using our PPMM-reg approach will in fact reduce the bias. The shadow variable approach is also limited to a single variable, whereas PPMM-reg can accommodate multiple A variables. Furthermore, the shadow variable must have larger support than the outcome variable that you're trying to model. So finding a shadow variable for Y can be impossible, actually, in some situations. It's fairly constrained. It's a powerful approach. It can improve inference, but the assumptions that it's making can be hard to justify in some of these cases. And the support issue is just kind of a fact. Okay, the A variable has to have larger support than your outcome. So it's a little bit limited in that regard. And we view the PPMM reg as a more general approach to this problem. So we conducted a simulation to evaluate our approach empirically and compare it to all these other competing approaches. We generated three finite populations of size 100,000 with values on Y, Z, and A. And these different populations reflected different strengths of the correlation of that auxiliary proxy X with the outcome variable of interest Y. So those different correlations were 0.2, 0.5, and 0.8. We then selected a probability sample using simple random sampling under ignorable selection of size 5,000 and a separate non-probability sample of size 500 from a given finite population as we were replicating the simulation scenarios. The probability of being selected for the non-probability sample was a varying function of Y and A, so that allowed us to simulate different scenarios. How big of a role were Y and A playing in the probability of being selected for that non-probability sample? And again, we use simple random sampling for the probability sample. Overall, we evaluated 27 different scenarios, and we can broadly group those into four larger sets. This is what those sets represent. The first general set of scenarios was ignorable selection with an actual shadow variable. The second set of scenarios was ignorable selection without a shadow variable being present. The third set of scenarios was non-ignorable selection with a shadow variable. And the fourth set of scenarios was non-ignorable selection without a shadow variable. And you can see the different number of scenarios based on the different correlations of X with Y from each of those different possible sets. Okay. We repeated the sampling process where we draw a pair of samples each time through the 5,000 prob sample, the 500 non-prob sample. We repeated that sampling process 1,000 times for each of these 27 scenarios. And then we evaluated all possible estimators that I defined earlier, in addition to the raw unweighted estimate where we don't make any adjustment whatsoever. And the mean of Y based on the probability sample was the benchmark in each case. So that was our target for the overall inference. Okay, so in terms of the simulation study results, that first set of simulations where we had ignorable selection with a shadow variable, this graph that you see here on the right is showing you the empirical bias associated with each of these estimators. So you can see those top two options are the probability sample estimate and then the naive non-probability sample estimate without any kind of adjustment. You can see the significant bias in that estimate if you had just done nothing and taken the raw estimate of the mean based on the non-probability sample. Then you see all the ignorable estimators, mass imputation, inverse propensity weighting, doubly robust, PPMM reg with phi set to 0, which is the fully ignorable case. And then the SMUB approach with phi set to 0, they all do very well as expected because those are designed for the ignorable setting. But PPMM reg and the shadow variable, because we actually did have a shadow variable present here, they also do very well. And you can see how they perform very similarly in this particular case. Okay. Now, the other estimators, PPM reg in general, does very well as a general approach. But SMUB and SMUB with phi equal to 1, they deviate a little bit in terms of their bias because they're designed to allow for non-ignorable mechanisms, and this is a fully ignorable selection mechanism. So all the estimators that assume an ignorable mechanism perform well as expected. Furthermore, the 95% confidence interval coverage or credible interval coverage for most of the approaches looks close to nominal, so that looks good. The SMUB setting with phi equal to 1 because that's fully non-ignorable performed the worst. And the confidence interval width was higher for all estimators as the strength of that auxiliary proxy decreased. So we had more uncertainty in terms of the estimate as the auxiliary proxy became a weaker predictor of that variable of interest y. The second set was ignorable selection without a shadow variable in that setting. And so here we have different simulations in terms of scenarios, in terms of that relationship of that variable A with the probability of being selected into the sample. Okay, so here again, A is not a shadow variable, so it does relate to sample selection even after you condition on Y. And you can see the odds ratios relating A to selection defining the two panels of this particular plot. Overall, both plots look very similar. So the strength of that relationship of A with the probability of selection doesn't seem to be a huge deal in this case, but the estimator used certainly matters. So again, the methods that assume ignorability or transportability produce unbiased estimates and good coverage. You can see that dashed line and where all the bias estimates actually lie. The PPMM-reg approach with phi equal to 1 and the shadow variable approach are biased as expected again, because in this case, we do not have a shadow variable. And you can see in this kind of third general row here how they essentially mimic each other. So they're behaving very similarly, those two different approaches, PPMM-reg with phi set to 1 and the shadow variable approach. And then PPMM-reg and SMUB, which consider many possible mechanisms, using uniform 0-1 draws, not setting phi to 1, but starting with random draws of possible values of phi, because we don't really know what phi is based on the data. They're not associated with as much bias as the shadow variable and the PPMM-reg approach with phi fixed to 1. So you see reasonable performance and not a whole lot of bias, although there is some there. Okay, so overall, pretty good performance in both of these ignorable scenarios, regardless of whether you have a shadow variable. But you can see how the shadow variable approach and PPMM-reg with phi fixed to 1 break down if A is not actually a shadow variable. The third case, which I would argue is the hardest case to deal with in practice, is where you have non-ignorable selection and you have a shadow variable present. So that's our third set here. Here, only the PPMM-reg method with phi set to 1 and the shadow variable approach produce unbiased estimates and close to nominal coverage, regardless of the scenario. Here you see the two panels indicate the dependence of selection on Y, because we're allowing for non-ignorable selection in this case. So you can see that if you look at that bias equal to 0 line, PPMM-reg with phi equal to 1, the shadow variable approach, and of course the probability sample estimate, those are the only approaches that really do well no matter what. You see now that all the approaches assuming ignorability start to deviate away from that bias equal to 0 line, the empirical bias line. Here you see the good performance of the shadow variable related approaches. PPMM-reg in general with uniform 0-1 draws still does okay, but not as good as we would like to see with the shadow variable being operating here. SMUB performs okay, but not as well as selection depends more on Y in the second panel here. And same thing here for SMUB with phi equal to 1. Not as good as the shadow variable approaches in PPMM-reg with phi fixed to 1. So here is where the methods that assume ignorability and transportability really break down when there's a non-ignorable selection mechanism. And PPMM-reg with phi set to 1 really does a nice job, even if we don't know if A is a shadow variable for sure. But here we have an actual shadow variable operating in the way that we simulated things. And the general PPM-reg approach does a little bit better than the ignorable scenarios, but not quite as good as simply fixing phi to 1. And then the fourth set is non-ignorable selection without a shadow variable, so where we don't have a shadow variable in A. Here, both PPMM-reg and SMUB methods consistently achieve the closest to nominal coverage. The methods that assume ignorability tend to have low coverage of the intervals. The exception is the IPW approach, and for some scenarios, the doubly robust approach, which show over coverage due to extremely large interval widths. And any methods under the case where we don't have a shadow variable that assume A is a shadow variable show severe undercoverage. So you can see that PPMM reg with phi equal to 1 and the shadow variable approach, they really do poorly in terms of coverage, especially as A has a stronger relationship with selection. We get far away from that nominal 95% coverage. But in general, PPMM reg is doing a pretty good job here in terms of confidence interval coverage overall for this non-ignorable selection without a shadow variable case. So if we just summarize what we found in these four sets of simulations, if one is to assume an ignorable selection mechanism, the doubly robust and mass imputation approaches perform well. In addition to PPMM reg and SMUB with phi fixed to 0, as we would expect, since that's the fully ignorable selection case. Under non-ignorable selection mechanisms, whether or not A is a shadow variable is of critical importance. If this is true, then the PPMM methods with phi set to 1 or the shadow variable approach perform well. If this is not the case, then the PPMM-based methods with those random uniform draws of phi tend to perform well. But mass imputation, assuming transportability, performs very poorly. In terms of interval width and coverage, having stronger auxiliary proxies is generally always important for these PPMM-based methods. And the key thing again to remember is that the SMUB adjustments, they just give you an adjusted estimate of your mean. That's what you're focused on. Unlike PPMM reg, they don't give you imputed values in your probability sample. So they're less attractive for subsequent analysis goals, where once you have those imputed values, you can do whatever kind of analysis you'd like to do. So that's an important distinction here. Okay, so that's simulations. We also wanted to see how well the approach would perform using some real data sets. So the first case study we looked at was looking at some real data from the National Survey of Family Growth. Here, the goal was to estimate the mean number of months worked in the past year for the target NSFG population, which is people between the ages of 15 and 49. And the selected sample that we were considering in this case from the larger NSFG sample that we looked at was smartphone users with less than high school education. So in this setup, we looked at smartphone users with less than high school education as our selected sample, obviously a very selected sample. And then we thought of the remainder of the NSFG data as the companion probability sample, or the remainder of the population where we're trying to impute missing values on this variable of interest. So really, you can think of this example as a superpopulation modeling example, as it's called, where you're trying to fill in missing values for all the non-selected cases in your population based on that imputation model. And then you try to estimate the overall population mean once you have that entire data set filled in. So here, based on the original NSFG probability sample, we knew that the population mean was 7.61 months worked. So that was our benchmark. That was our target. But then we just deleted that variable for everybody who was not a smartphone user with less than high school education. And we fit a model to that selected sample to try to predict what the number of months worked was in the past year for everybody else in the NSFG sample. So the first part of this application, we want to see how well that adjustment that I outlined earlier for the imputation model coefficients performed for our target imputation model for imputing missing values on number of months worked. So the target imputation model that we wanted to use used gender, male versus female, and age as the key predictors. So those were our Z variables in the imputation model for the number of months worked. So you can see in the selected smartphone sample with less than high school education, what the estimates of the coefficients in that model were in a model predicting the number of months worked. Okay. Then in the full population column, that's the actual values of those coefficients if we hadn't deleted the Y variable data for everybody in the NSFG sample. So the point here is to see the clear bias in some of these coefficients coming from fitting that model to the selected sample of smartphone users with less than high school education. Then the final column shows the MUB adjustments of those imputation model coefficients for that potential selection bias. And so the point that I want to make here is that the MUB adjustment is moving those biased coefficients from the selected sample in the correct direction of what that model looks like for the full population in this application. So you're seeing the shift of each of those selected sample estimates in the right direction of those full population coefficients, which is important for the sake of improving our imputations. Okay, so the bias in those imputation model coefficients based on the selected sample is getting reduced by that MUB adjustment. And you can see the 95% credible intervals there as well for those adjusted coefficients. Okay, so we used then the adjusted models based on this kind of approach to impute Y, number of months worked, for all those non-selected cases in the full NSFG dataset, computed the means in each of these processes, and then compared those overall estimates or the posterior mean for Bayesian approaches to that known truth of 7.61. And so you see, we evaluated the naive approach, where if we just estimated the number of months worked, the mean, we get 4.41. Remember, the truth was 7.61. So the naive estimate, based on the selected sample, way off. Okay. What if we use mass imputation? We get a lot closer. So using standard mass imputation, assuming transportability, 7.11 would be our mean. You can see the corresponding credible interval falls a little bit short of that truth, 7.61. We've also included the relative bias in each of these point estimates here. The PPMM reg approach, which allows for that non-ignorable selection, really got us close to that estimate. The interval is a little bit wider than we see with the doubly robust approach, but in terms of the point estimate, we have the least relative bias from that PPMM reg approach. Then you see the SMUB adjustment, which calculates the mean based on that standardized measure of unadjusted bias, its relative bias, and then you see the doubly robust approach, which again gets us pretty close with a tighter interval and the second lowest relative bias. So certainly a competitive approach relative to PPMM reg. In this particular case, we couldn't fully evaluate the shadow variable approach because no predictors had larger support than this particular outcome variable. So again, that's another limitation of using the shadow variable approaches. So pretty good evidence here of the PPM reg approach being competitive and getting close to that true mean. The second case study that we looked at was from the 2023 Census Household Pulse Survey. And here the goal was to estimate the mean PHQ-2 depression score that was measured in the HPS based on using the 2023 National Health Interview Survey as a companion probability sample. Now, the depression score was measured in both of these samples, but we assumed that it was not in the NHIS, again, so we could have a benchmark and see how well we did relative to that benchmark. The Z variables were several harmonized sociodemographic measures in both of these data files, and the A variable was a PHQ-2 measure of anxiety. So you can think of this again, what would be a good A variable in these applications? Well, here we're essentially grabbing what could be thought of as another Y variable. We might also want to fit a model to anxiety in addition to depression. Here we're grabbing anxiety as a highly relevant predictor of depression, but not one that was in our imputation model of interest based on these harmonized sociodemographic measures. So these A variables could be dependent variables from other variables that you're trying to model as a part of a larger application. Okay. So the HPS in this case was the selected non-probability sample, which had about 62,500 observations, and the NHIS was the companion probability sample without, in double quotes, the Y variable, because we took it out just for the sake of this evaluation, about 29,500 cases. So here are all the different estimators that we considered, in addition to the estimated means based on that approach, and then a 95% confidence or credible interval depending on the approach. What's very interesting to note here is that the truth, the weighted mean based on the NHIS, was about 0.56 on that PHQ depression scale. The naive estimate based on the household pulse survey was about 1.17. And you can see that if we just treated the household pulse survey like a simple random sample, a big SRS, very tight credible or a confidence interval, but way off from the true mean. Okay. What's interesting is that the weights that were provided for the household pulse survey moved the estimate in the wrong direction. So there were weights developed for that household pulse survey to try to speak to the larger population. For this particular mean, they moved the estimate away from the truth. And then you can see the 95% confidence interval in that case. Mass imputation, assuming transportability, got us closer. It got us moving in the right direction where the mean was about 0.74. You can see the confidence interval. Inverse propensity weighting, very similar type of adjustment, similar type of confidence interval. We tried the doubly robust approach that gave us a good point estimate, but we couldn't compute the standard error. Rebecca and I were looking into that. We couldn't get a reasonable standard error in that case, and it wasn't clear why in the software routine that we were using. So that's why you see the asterisk there. We're still looking into that. Um, PPMM reg approach did very, very well once again. So it almost nailed the true value. And you can see that the credible interval is roughly centered at that true value and reasonably narrow. If we fix phi to 1, instead of taking random uniform 0, 1 draws of that sensitivity parameter, we just fix phi to 1, which remember is mimicking the shadow variable approach, we actually over adjust. So we go a little bit too far in the negative direction there. See a pretty tight interval, but the point estimate itself is really a bit too far adjusting in the negative direction. And then the SMUB approach gets us pretty close as well, gets us to about zero point 0.6 with a reasonable credible interval. So we see the significant bias in the naive and weighted estimates based on the HPS, and we see how PPMM reg again gives us a reasonable adjustment using the real data. Okay, so just to wrap up with some conclusions here, we find general support for the effectiveness of this proposed PPMM reg approach, which can be applied for mass imputation or superpopulation modeling applications across a variety of scenarios. The shadow variable methods can be thought of as a special case of the proposed PPMM reg approaches where that phi parameter, that sensitivity parameter is set to 1, fully non-ignorable selection. The PPMM reg approach can accommodate multiple A variables with varying support for better performance. If selection actually depends on A when you condition on Y and Z. And the SMUB method does compete well in a variety of different scenarios, but again, it doesn't impute values. So it doesn't give you a filled-in probability sample that you could subsequently do whatever you want with. So that limits studies a little bit where you'd want to use the imputed data in a variety of different ways. The doubly robust and mass imputation methods tend to perform well under ignorable selection mechanisms. The doubly robust methods also perform well in the case of non-ignorable selection as long as A is not a shadow variable and when the dependence of selection on Y is a little bit weaker. If a shadow variable exists, the performance of the doubly robust methods becomes worse, and performance can also worsen as dependence on Y increases. In practice, we would recommend implementing the methods that we've evaluated here and comparing the inferences that you would make across these different methods in light of the empirical evidence that we've demonstrated. And we find general support for the use of that PPMM reg methodology, but we'd like to see it evaluated in other applications. So for future research, the PPMM reg approach does assume that the data are ultimately governed by that bivariate normal pattern mixture model with the auxiliary proxy defined by A. And it'd be good to see if that bivariate normal model doesn't hold, how well would we do here with this performance? In that previous article, we describe adjustments that could be applied to the coefficients of a probit model used to impute a binary variable, but similar adjustment approaches would be needed for other types of Y variables. My student, who I believe is here in the seminar, Daegi, she is using that probit modeling approach in the case of a selection model in another application that she's working on, and she's finding very good results there as well. So that's promising. We also assume that the model used to define that auxiliary proxy has been well specified, so we're not misspecifying that model for X. Additional work should consider what happens if we misspecify that model for X as a function of A. And finally, we would call for additional applications of this approach in a variety of mass imputation problems. Again, Daegi is working on that for her dissertation right now, but really to evaluate the performance of this kind of approach in a variety of contexts outside of those that were considered here. And we do have software available for you to use to implement this PPMM reg approach. If you're interested, you can certainly reach out to me and I'll share that code with you. So again, if you have any questions, please feel free to send me an email. Happy to take questions here as well after the talk is over. And again, at the end of these slides, assuming we can eventually share them, I've included references that I cited throughout the talk here if anybody would like copies of any of these articles talking about these approaches. And the paper describing this general approach that I've outlined here is currently under review. And I'd be happy to share this paper with anybody if you're interested. Okay, so that's all I have to say. Happy to take any questions about the general approach or any aspects of it. And thank you for your attention.
Well, thanks so much, Brady. That was super interesting, and I will definitely bug you for that paper.
Okay.
And just to clarify, we will be sharing the slides and the recording, once we get the accessibility stuff all finalized. So keep an eye out for that. But yeah, any questions for Brady? I think we have time for one or two.
Hello. I do have a question. Sorry.
Yeah, go ahead, Victor.
Yes. Hi, John. How are you? Brady, awesome presentation. Really enjoy it. In the specific scenario for number two, I was really curious about polls. I analyzed, no, I didn't analyze, but I review a lot of papers because a lot of papers use that specifically when, they were talking about the pandemic of mental health disorders during, the second pandemic and everything. In the comparisons that we're doing because we didn't have a good baseline, right? The issue with polls was at least for the first phases of the survey itself was the response rate, which was around 2% compared to National Health Interview Survey, which is around 60%. I was really interested when you were mentioning this. Do you think that had an influence also in how far it was because they did adjust it to the census population, but adjustment just to meet the distribution of the demographics doesn't mean anything when you actually
Well,
it's not the
yeah,
measure for the outcome that specifically depression that we were looking at the moment.
yep, that's exactly the issue is that the weights that they computed for the pulse survey, they're following that kind of calibration approach.
Right.
And when you just weight to these control totals, you're assuming a 100% ignorable selection mechanism. So any kind of weighting adjustments like that assume ignorable selection. Once you have those covariates available that are used to develop the weights, the missingness is only occurring at random. That assumption underlies every weighting approach.
Right.
So that's why we saw this really interesting case where once you applied those weights, assuming ignorable selection, the estimate went in the wrong direction of what the truth should be. And that can happen when you assume an ignorable mechanism, but what's happening is really not ignorable as a function of that variable of interest. So Rebecca and I, we triple checked this. We were like, wait a minute. But those weights were literally moving the estimate away from what the truth would be.
Right.
And that can happen because you're assuming ignorability.
Thank you.
Yep.
All right, I think we have time for one more question.
Can I jump in if that's okay? Oh,
Yeah, go ahead, Aaliyah.
yeah. Hey, Brady, thanks so much for this. My first question is just a quick clarification one. It's probably just I missed it. Uh, the auxiliary A variable, that's coming from the reference sample or your
It's in
sample?
both.
It's
Yep.
in both. It's in
We have
both.
that A variable in both. Yep.
Okay, so this is helpful. So my question almost is like in terms of doing this kind of more practically, like um, would you be how much should the auxiliary variable inform your selection of a reference sample to do this? Does that make sense? Like having a good
Yeah.
auxiliary variable like that.
Yeah,
Um,
in many cases, it's going to dictate what reference samples are even available to you because you want to have values on that auxiliary variable present. So it's thinking about, like I mentioned, a really good way to think about it is like you might have a bunch of dependent variables that you're interested in. And those dependent variables may not necessarily be predictors in models for others, but they might still be relevant. So you could use that to predict, but it has to be present, at least in aggregate for both your reference probability sample and your selected sample to be able to employ this methodology. So if a particular probability sample doesn't have that A variable, kind of rules it out. So you have to find another probability sample that would have a measure of that A variable in this case. And that can limit, certainly, I do not disagree that it's going to limit what choices are out there. And as I've talked about with these methods and other presentations, I think the hardest part of all of this is finding good probability samples with the necessary measures of Z and A. I think that's the hardest part of this entire problem is finding that kind of good auxiliary information that's available in a probability sample that can give you nice population estimates. I think that's the hardest challenge, honestly. So,
yeah, thanks. Yeah, yeah. This is helpful because I was just trying to think about it in terms of like trade-offs.
yeah,
You're gonna have samples that probably have a lot of nice other features, but if they're yeah, they don't have
yeah.
the some of the really, really key predict well, not predictor. predictor in the auxiliary sense. Right, right.
Yep.
Thanks
Yep.
for that. Yeah.
Yep. Yeah, we go on and on about that in the paper itself. So there are a lot of issues there. So yep.
All right. Well, I think we're at time, so we'll go ahead and close things there. But thank you so much for that great talk, Brady. And folks, stay tuned. We will get the recording and the slides out. But if you have questions, please don't hesitate to reach out to SBCCC. We can certainly connect you with Brady to get additional clarification or some of the materials that he's referenced. So.
Yeah, and again, just feel free to email me directly if you would like. That's fine. I'd love to take questions and comments, and I'm happy to share these materials. So, yep.
Didn't want to put you on the spot, but I appreciate the
No,
offer.
I'm happy to do that. So, yep.
All right. Well, thank you guys, and we'll see you in the next meeting.
Okay. Thanks, John. Thanks, everybody.